Okay.
Welcome back, everyone, and good morning or afternoon. Yeah, afternoon actually. We're going to continue. Last time we discussed the first law of the ideal gas law, right? And we did a couple of examples on the ideal gas law. And today we're going to discuss work, heat, and the first law of thermodynamics. Okay? And so we discuss work, heat, and the first law of thermodynamics. So the first law of thermodynamics relates to the internal energy, which we would just call the thermal energy in this class, which has to do with the motion of all the constituents, all the particles. So the average kinetic energy of all the particles multiplied by the total number of particles, that would be our thermal energy. So imagine you have all the oxygen molecules in this room, assuming the room has only oxygen. It's mostly nitrogen, right? Air. So let's say it's just oxygen. You count, you look at every oxygen molecule, what's the kinetic energy? You know the mass, so 1/2 mv squared, that's your kinetic energy. Do that for all the molecules, and you will get the thermal energy in this room. The thermal energy happens to be a reflection of the temperature of the room. More temperature, the higher the temperature, the more the thermal energy. The only way to change the thermal energy is by changing the temperature. Okay? If the temperature doesn't change, the thermal energy does not change. And the first law of thermodynamics asks the question, or answers the question, how do we change the thermal energy of the molecules in this room? One way is to do work. Okay? So we'll keep in mind a gas in a piston or in a cylinder, and we ask, how do we change the kinetic energy of the molecules of that gas? One way is to do work on it, and another way is to add heat or subtract heat from it. Okay? And so we're going to focus on work, and then heat, and then state the first law of thermodynamics. So work. Work is from physics, from mechanics. What was work? Force applied over distance. Yeah, loosely speaking, just force times distance, basically, right? Yeah. So, work, heat, and so we're going to have a gas in a piston, and I'm going to orient my piston horizontally so that it's along the x-axis, and then we will go from there. So here is the cylinder. Looks like this. This way. And let's say the gas molecules are here. They're bumping into the piston. And let's say the piston has a cross-sectional area A. Area is A, right? So the gas molecules, they're applying a force from inside, and the environment is applying a force from the outside into it. So there is a force on it, the force on the gas or on the piston here, F on it, and then there is the F by the gas molecules, right? By the gas molecules. So we ask the question, what's the work done by the gas molecules? So let's say the cylinder, the gas molecules, they're able to expand. Okay, let's just talk about the expansion case. So they're going to be, they were here, and now they're here, and so they were able to move the piston at distance x, right? So we're able to move the piston by a distance x. Is that clear? So the gas molecules expanded. They have a larger volume. So the gas expanded has a larger volume, it's occupying a larger volume. The question is, how much work did it do? Well, the work done, we call it dW, a small amount of work. This is the work done by the gas, let's say. I put by just to be absolutely clear. It would be the force by the gas, right? Times the displacement, d, right? Clear? Force times distance or displacement. But the force, how is it related to pressure? Pressure is force divided by what? Area. So force is pressure times area, right? So it would be, the force would be the pressure times the area times dx. But what is the area times dx? The cross-sectional area plus the area volume times, yeah, that's the volume of that portion. dV or delta V. In this case, I'm calling it d, so it's going to be p times dV. This is the work done by the gas. And so, the work done by the gas is going to be P dV integrated from some initial volume to some final volume. That's the work done by the gas. On the other hand, the work done on the gas, so there are two forces. There's a force from here, that's the force on it, and then there is a force by it. And the piston is always near equilibrium. So there are two opposite, right, forces. So for example, if I push this chair, if I push the chair this way, I'm doing positive work on the chair. But the force from the chair is a Newton's third law pair on me. And so its force is this way, but the motion is that way. It's going to be negative, right? So the work done on the gas is always going to be equal to the work done by the gas, but with a minus sign. So this is the work done by the gas. It's this integral from V initial to V final, P dV. The work done on the gas, which is going to be exactly the same, but with a minus sign. Our book uses the convention. They just say W. And when they say W, they mean the work done by the gas. It's almost 50-50. Other books, W for them means the work done on the gas. So you just have to pay attention to what we do. In my statements of quizzes, tests, homework, I try to be explicit. I say, what is the work done on the gas? Or what is the work done by the gas? Okay? Work done by or on could be positive, negative, or zero. So let's look at the work done by the gas. It would be zero if the piston doesn't move. So it's zero if the volume doesn't change. Okay? The work done on the gas is also zero if the volume doesn't change. Now, suppose the gas expands. So the volume increases, right? So the work done by the gas in that case, if the volume gets larger, is it positive or negative? Positive. The gas wants to expand. So it got what it wants, so the work done by the gas would be positive. On the other hand, the gas is in this cylinder, and it's pushing, trying to get larger, and somebody compresses it, so it got smaller, so the work done by the gas in that case is negative, right? So the container shrinks, the work done by the gas would be negative. The reverse is true for the work done on the gas. If the gas expands, the work done on the gas would be negative. If the gas shrinks, the work done on the gas would be positive. Yes. The area times the cross-sectional area times this. So if you think about it, this area times this would be the change in volume here. And so these are this is the work done, how you would calculate. And we're going to spend some time calculating the volume for a second. Now, I also want you to notice whenever you have an integral, P dV, so it would be, the integral represents the area in the PV diagram under the curve. Right? So let's do the first example here. I'm going to, it's in the notes, I'm going to just try to sketch it. And that helps slow me down actually when I draw the problems on the board. So here is the problem. Here is the volume, it's in cubic centimeters. The pressure is going to be in kilopascals, means 1,000 pascals, each of them. Here is 100, here is 200, and here is 300. Okay, 300. And this is the volume of the gas, 500, 1,000, 1,500. gas starts here. Then the volume will increase. Will increase to 100. Let me just do this. Going to follow this line like this, and then it will go horizontally like this. The question is, what's the work done? On the work done, let's say the work done by the gas first. Let's say find W by the gas. Question, the first question is it going to be positive, negative, or zero?
Positive.
Positive because?
Because it's going.
Expand.
Yeah, it's expand.
The volume of the gas got bigger. The gas is inside. Just think of it, you're inside, you're trapped in that container, and you're pushing against it, and you get what you want. You get larger, so you have done positive work. So the gas actually did positive work. The work done on the gas would be negative. It would be the same value exactly, but with a minus sign in front. Now, how much work is it? You just have to calculate the area under the curve, the area here. The area bounded by this curve from the top, these vertical lines, and then the x-axis, so it's this. Now, how do we calculate that area? Well, you got triangles and rectangles, you can just add all the areas. I'm not going to go over that. Just be careful, cubic centimeters, you need to convert it to cubic meters. Kilopascals needs to be multiplied by 10 to the 3 to be pascals, so that your result will be in joules. Okay? So you can do the area, I'm not going to do it. And it turns out to be W by the gas, 250. The work done on the gas is minus 250. I know, I didn't do it, but I trust you can do it. Just rectangles and triangles. You can do that. Okay. No integration in this case. No integration in this case. We have essentially done an integral by finding the area, but it's a simple area. Okay. So, what is the work done for the different processes? Yes?
So you're saying that the volume increased, so the pressure, what do you mean? Like, did the pressure decrease?
No, the pressure was 100, it increased, right?
Uh-huh.
And then it stayed constant here.
So the volume increased and the pressure increased?
For some portion of it, yeah. In this case, the
Uh-huh.
volume and the pressure both increased, yeah.
Uh-huh.
But here, the volume increased, but the pressure remained the same. Yeah. But the important part for the work, whether it's positive or negative, is whether the volume increased or not. So in this case, did the volume overall increase or not?
Yes.
It was 500, it became 1500.
Yeah.
So the volume increased, therefore the work done is positive.
Okay.
Yeah. And then how much is the work? That's where you have to calculate the area. And the area would just be the area. Yeah. Yeah.
Would the work by always be the opposite of the work on?
Yes. Yeah. Always there is a there. If one is positive, the other is negative, and their magnitudes are the same. There is no question. I'm going to talk about the different processes and how much work is done. Which processes have we talked about? We said there are 4 main ideal gas processes that are considered. Isochoric, that's where the volume is constant. Good. Second one, isobaric, which is pressure remains constant. And isothermal, temperature remains constant. And then adiabatic, which we didn't discuss, but we said there is this quantity called heat, is 0. No heat enters or leaves. Okay? So we're going to do it for the first 3. The fourth one we're going to leave alone for now. Okay? So for isochoric, it's the easiest. So in an isochoric process, so let me just conserve space right here. Isochoric. Since the volume doesn't change, the work done is 0. Okay? W is just 0. And notice I didn't even say W by or on, because it's just work is 0. 0 or negative 0, they're still 0. isomorphic. Sounds good? So it's like you take this wall and keep pushing on it. You don't move the wall, so you didn't do any work. Isobaric. Isobaric. Let's start with the work done by the gas. Here's the definition right there. P dV integral from V initial to V final, right? That's the integral I need to do. But it's isobaric, so what do I know about the pressure? It's constant, it doesn't change, so we can pull it out of that. So meaning this, I have this P. Okay. What's the integral of dV? V. And when you evaluate it between V final and V initial, you get V final minus V initial. What is final minus initial? Delta V. So it's the change. So this one is just P times delta V. That's all. P times delta V. Which part of this graph was isobaric? 1000. This one. This one. So it would be, think about the area in this case. What's the area for this rectangular part? It's P, this P, right? Times the change in volume, because you have to multiply by this. It's the height times width. The height is P. The width is final minus initial, 1500 minus 1000. So that's that one. So that's what this one is telling us. And the work done on the gas is, in this case, will be what? For isobaric. So, yeah, so it's just going to be that. P delta V, but with a minus sign. Let's put it in blue. Not much to do there. For isothermal is where we actually have to do something. Okay. Let's do now the work done in an isothermal process. So isobaric, isothermal is the next. For isothermal, remember how isothermal looks like. Here's V, here's P, here's the initial, and here is, let's say, V final. How does an isothermal process look like? Yeah, like this. It's 1 over. So let's say this is isothermal. So in this case, the work done by the gas, on the gas, they're both the area, but one is positive, one is negative. So it's got to be this. This is the area, right? That's the work. Magnitude of the work is just going to be the area. Just a follow-up question. Follow-up question. In this case, let's say the initial is here, the final is here. Did the gas, in this case, in the one I drew here, expand or contract? Expand. So the work done by, is that going to be positive or negative? Positive. The gas got what it wants. It expanded. The work done on the gas, is it going to be positive or negative? It's going to be negative because the gas expanded. Okay. Now, how much is the work? What is the work? I need to find a symbolic expression for it. And it's going to be some function. Because you have this 1 over, you have to integrate that. So here it is, it's going to be the work done. I'll put by first. It's going to be P dV, the integral. Now I can't pull P out of the integral. Can't, because it's not constant. Pressure, you see here? Pressure is changing, it's decreasing. So I can't just pull P out. So that's a problem. And at the same time, I can just integrate this because P is a function of P. So what am I going to do? Yeah, use the ideal gas law. So using the ideal gas law, you can replace the pressure by what?
1 over V.
Yes, Because the ideal gas law says TB equal to nRT, then P will be nRT over V, right? Okay. So nRT over V dV. Seems like I made it worse because I have more symbols now. Yeah. So notice, N is constant, R is constant, and T is constant because it's isothermal. T is constant. So you can pull those out of the integral. Okay. That's the advantage. So you get this. Let me go to the next. Now, N, R, T, the integral of V you can pull out. It's not constant. So dV over V. Now I put my limits. Integration T initial. Right? You see why T is pulled out again? Because it's isothermal. Where we know it's an isothermal process that we're calculating the work for. So T is constant. Okay. Continue maybe horizontally. What's the integral of this? 1 over T? That's for 1. Okay, so nRT ln of V evaluate between V initial and V final, right? V is positive. So natural log, so you have ln V final minus ln V initial. What does it become?
ln V final over V initial.
Yeah, it's going to be this. nRT ln of V final over V initial. And that's the W by the gas. This formula applies only when? Isothermal, right? Yeah, you can't just see a formula and plug in numbers there. You have to think about under what circumstances did we derive this equation. We got it by assuming temperature to be constant. That's how we got to this step. So this is for isothermal. How about the work done? Let's do W on the gas. Going to be what? It's going to be the same thing, but with a minus sign. Yeah, minus nRT ln emission. Isothermal. Now, I want you to notice the natural log of something is positive. When is the natural log positive? Ln of something would be larger than 0 if that something is more than 1. And what's the natural log of 1? 0. And natural log of less than 1 would be negative, right? All the way. It goes to negative infinity at 0. Closer to 0, you go to minus infinity. So this natural log can be positive, negative, or 0. Notice, if V final is larger than V initial, then the ratio would be more than 1, right? If V final is larger than V initial, the ratio would be more than 1. It means the gas has expanded, so this natural log will be positive, and so the work done by the gas will be positive. And then, of course, the reverse is true. Work done on the gas. Let's look at an example of this example. So we have a cylinder containing nitrogen gas, and we have 0.25, a quarter mole. So consider here's a container. Here's the container. We have N is 0. The number of moles N is 0.25 moles. And then the initial temperature is, the temperature is 80 degrees Celsius. And we're going to compress it. So compress until the volume takes half. much work was done on the gas to make this happen. So find work done on the gas. How do I do it? Yes. Isothermal, yeah. It's an isothermal process, yeah. Did I state that explicitly or no? No? So let me just say, state it, isothermal. It's an isothermal. So if the temperature here is 80, what's the temperature here? Still 80, right? Because it's isothermal. So how do I want the work done on the gas, so W on is equal to what? Actually, let me ask before we even count it. Is the work done on the gas going to be positive, negative, or zero? The work done on the gas is going to be negative?
Positive.
Positive? Or negative?
Positive.
Positive? Okay. On the gas. Yes, the work done on the gas is going to be positive. The work done by the gas is going to be negative. The gas shrunk, so it did negative work. So the work on it is actually positive. I think you're the one pushing the cylinder or the piston. You did what you wanted. You're pushing it down and it went down. You compressed it. The gas, think of who is inside there. Who is inside, they want to have a larger space, but they actually were shrunk. They got smaller space. They did negative work. But this one specifically says what's the work done on. Well, let the math do the work for us. Here is the math. It says W on. It says it's minus nRT natural log V final over V initial. Okay, let's plug in some numbers. Minus this minus sign here. This minus sign will actually make it positive. This minus sign will be the thing that will make this work done on the gas positive. Let's see. Here's the minus sign. N is 0.25. R is 8.314. What's the temperature?
353.
Yeah, but don't plug in 80. You need plus 273. It has to be the temperature in Kelvin. So, and 80 plus 273 is 353? Yes, 353. And then natural log of what? What's V final divided by V initial? 1/2, yeah, V final over V initial is 1/2. And natural log of 1/2 is actually negative 0.6 something. So this number is negative, and there is this minus sign, that would make it overall positive. So this is going to be plus. This is 508 joules approximately. So the work done on the gas is positive. What if I ask you what's the work done by the gas? Negative 508, yeah. Once you know the work done by, either one, on or by, the other one is just a minus. Okay. Now work depends on path. Work depends on path. So for example, if I say, here is B, here is P, here is initial, and here is final. This is initial, and this is final, right? If I just give you the initial volume, the initial pressure, the final volume, the final pressure, and I say find the work, you can't. Yeah, you cannot find it. Why not? Because you don't know the final. You don't know the math. Yeah. Did we do this? I don't know. What's the process for doing this, right? How did we get from here to here? Did we do this? If we did that, when the area is just here, the area here, did we go horizontally and then up? Maybe we did this, right? In that case, it's just this area. Did we do this, right? In that case, the area would be even bigger. So let's say 1, 2, 3. Which one is the biggest work? Three, the largest area, right? Is three. Sounds good. It's time to talk about heat. Notice work is macroscopic. It's a piston moving. You're pushing, you're applying some macroscopic force, and you're getting the work done. Something you can see with your eyes. Heat is the, so work, you transfer energy, right? You're doing work to change the energy of the gas, eventually. Heat, on the other hand, is the microscopic transfer of energy. So heat is the energy transferred between the system, or between a system and the environment as a consequence of the temperature difference. So, but it's microscopic. So if you put, again, hot coffee versus cold coffee next to each other, the hot one will cool down, and the cool one will warm up, and they will get to some final temperature. Now, heat is the energy transferred between the two because they had a difference in temperature. Okay? Because there was a difference in the temperature between the two systems. So heat will only transfer if there is a difference in temperature. If there is no difference in temperature, then it's already in equilibrium. Heat will not transfer from one system to the other. Okay? It always transfers from, what do you think, higher temperature to lower or lower to higher? Higher to lower. The higher temperature will lose energy to the lower temperature. Microscopically, I think I mentioned this last time. So I said energy, or thermal energy, is a reflection of the temperature. Higher temperature means the molecules are moving faster. Lower temperature, the molecules or particles are moving slower. So let's say you have a high temperature system and a low temperature system. The high temperature system, the molecules there are moving fast, right? The low temperature system, the molecules are moving slow. Put them next to each other. The molecules start to collide. The ones that are moving fast, they collide with the ones that are moving slow. On average, will the faster ones move even faster and the slower ones slow down, or they would come to some common average? The faster ones kind of slow down after collisions. The slower ones, they speed up after the collisions, and then they will average to some final kinetic energy, final speed. I think we agree with that, right? So yeah, just think of it as something at rest, right? In the extreme case, something at rest, something is moving, they collide. This one is already at rest. It can't go slower than that. It's at zero speed, and so it has nothing to do but to move. So that is the what's happening with heat. Higher temperature, lower temperature, the energy transfers at the molecule level. Whereas with work, you're actually compressing some big things, some pistons, some macroscopic processes. Okay. So heat, but historically heat was considered with let's say water, I want to warm it up. They say we add heat to it, but that heat was measured in calories. A calorie was the energy needed to raise temperature of 1 gram of water, 1 degree Celsius, from I think 36 degrees or something like that. Anyways, it was measured in calories. But then work was measured in joules. There was no connection between them. Now, how do they connect? Well, the Joule experiment connected macroscopic work to this microscopic quantity called heat. So it related the Joule to the calorie. Here's just a sketch of the experiment. You may be familiar with what I'm going to say now, calorimetry and this. May be familiar to you from chemistry. If it is, great. If it's not, I'm starting from the beginning. So if you have seen it, it might be boring a little bit, but that's okay. Always have trouble drawing this Joule experiment. So imagine you have a container here of some big bath of water. And you put it, let's say the temperature is 10 degrees Celsius. You put it on a stove and you warm it up. It will be 20 degrees Celsius, right? You warm it up by 10 degrees, right? On the other hand, if you stir the water very, very fast, it can also get warm. Okay? It can get warmed up. And you wouldn't know whether you warmed it by stirring it or by putting it on a burner. So here's the experiment. It did this. You have a shaft like this, and it has paddles. This is a paddle, and it's full of water here. This paddle here, this is another paddle, this is another paddle. And when you spin it, these paddles, they stir the water. There is a pulley here, and there is a rope, and that rope winds like this. And here is a mass M, and this is a height H. This mass has potential energy. As the mass drops, it will lose potential energy, right? And let's say by the time it gets to the bottom, let's say the potential energy relative to the ground will just be 0. And then let's say it's barely moving when it gets to the ground. So it had a certain amount of mechanical energy. When it fell, this thing was turning. And what happens is, all this energy, this mechanical energy that was lost, which is mgh, right? Mass times gravity times height, is reflected as an energy change in the water. The water warms up by a few degrees, by a certain amount. Okay? So then you say, okay, the water warmed up. I added a certain number of calories, right? It's as if I added a certain number of calories to warm it up by that much. On the other hand, this one lost this many joules. So this many joules are equivalent to this many calories. And that's how the calorie was related to the joule. So it says here, 1 calorie to 4.186 approximately. Now there is the kilocalorie. 1 kilo. 1 kilo calorie, which is 1,000 calories, and those are the same as 1 calorie with a capital C. 1 calorie with a capital C. And 1,000 calories is, of course, 4,186 joules. That's a given. So now we just have a way to translate from calories to joules. By the way, the food calories, where if you eat something and it says 100 calories, it's actually one of these,